Okay, so now we're going to start this recording here. Share the screen. We've got the correct textbook all uploaded here. You are screen sharing. Well done. All right, so now we're going to cover chapter 10.5 through the end of chapter 10. Try to do this in the best way possible so that you can use this stuff in your homework. We're talking about moment of inertia. The moment of inertia is a way of understanding how the mass is distributed for an object that's rotating. So it depends on the mass that's in the object, depends on where the mass is, so the distance to the mass, and the distance to the mass relative to the point of rotation, or the axis of rotation, I guess is a better way to say that. And also it depends, it depends on that distance squared, because in the previous section we learned from doing the math with the kinetic energy of rotation that this moment of inertia thing is going to be an mr squared thing for point masses. And so we're doing this for point masses to begin with. And if you have multiple point masses that are all going to be rotating around a single axis, then you can add those multiple point masses together and you get each one of them times their distance squared from the axis of rotation added together. So it kind of looks like this, I1. And if you have, let's say we have this situation with a barbell rotating. We're going to rotate it around the center of the bar. And so we have two masses that are equal distant from that center, and you're going to get mass 1 times the distance squared plus mass 2 times the distance squared. Both masses are the same, so it's just mass. Both distance are the same, so they're just r. But this becomes your moment of inertia if we consider those masses on the end to be point masses and the bar in the middle to have no mass itself. So we're considering the bar to be negligible mass. We're not counting it. In the second situation, we're going to rotate around this mass over here. So this thing is going to be swinging around with this one swinging all the way around and this one just kind of rotating on its center. Well, that has distance 0 from the moment of from the axis of rotation. So it's m times 0 squared. So it doesn't contribute to the moment of inertia. Or the other one has a distance of 2r. So we square that, it becomes 4mr squared. So this configuration, or this rotational situation, has twice as much moment of inertia as this rotational situation. What that would mean is this one would be more difficult to rotate than this one. But what if we have a strange shape of matter? We'll, just like in all things, we're going to break it down into tiny little masses and then add them all together using an integral. So here we have our differential mass, our tiny little piece of mass, and the distance that it is from the axis of rotation. Notice that this distance is the perpendicular distance, and that is always to be the case. You always want to take the perpendicular distance to that little piece of mass. And then we're going to move this little mass around and add up all the tiny little masses that we can. And we do that by using an integral over the entire shape of the object. Now, integrating over a shape is, we can call this an area integral or a volume integral, but it's quite difficult unless you know the mathematical formula for this shape, for this line that outlines this shape. If you don't know a mathematical formula for that, how are you going to put it in an integral, right? It's very difficult to do without a computer. And so we're only going to do this for shapes that we know the formula for. We're going to do this for shapes that are familiar to us. This is the summation, and then this is the integral that we're going to use now with a continuous mass. Well, here's a shape that we're very familiar with. It's just a simple line. The equation for a simple line is quite easy to work with. We can do integrals along the line, no problem. The integral looks like r squared dm, right? So we have the distance to each piece of our mass times the differential mass. Well, we have to figure out what dm is, and we have to figure out what r squared is, and we have to get those in the same independent integration variable so that we can actually integrate. So we start off with the dm. Well, this little piece of dm is going to have a little length of dx. So that starts off, the distance to it is going to be x because r is in the x direction. We're only in one dimension here. the total length of the rod is going to be L, and we're gonna have a rotational point around the middle, so it's going to go to L over 2 on this side and to negative L over 2 on this side. And we're going to define our mass of our entire rod here, the entire piece of material, whatever it is going to be M, and that's going to be equal to the linear density of it times the length. So we can define our linear density as the mass over the total length, total mass over total length. And if we take a derivative of this M here to get dm, then it's d of lambda L, because if you solve this for mass, you get this, and so we're taking this derivative of lambda times L, right? So our dm becomes lambda times dl, and dl is actually dx, and so we replace dm with lambda times dx. We already discovered that r is going to equal to x, so we get x squared lambda dx here, where lambda is a constant, and lambda we actually know is the total mass over the total length, so we can put that out in front. We can pull that out in front. So when we go to do our integral, we're integrating from negative L over 2 to L over 2. We're going to take out the lambda. It's going to come out of the integral. And then we're just integrating x squared dx, which has an integral of x cubed over 3. And then we go ahead and plug in our L's here, and we get 1/12 ml squared in the end. So now we know what the moment of inertia is for a thin rod or a thin bar of some length L with some total mass M, where the mass is distributed evenly. We did assume that the mass was distributed evenly when we did this up here, the uniformly distributed mass. And that is now something that we can remember. If we ever have a thin rod that we're rotating around its middle, we can say the moment of inertia is 1/12 times the mass of the rod times the length of the rod squared. Good. Well, what if we do it with the axis at just one end? So instead of rotating it around the middle, we're rotating around this end. Well, everything actually stays the same in the integral, except for the integration limits. We're now going to integrate from 0 to L, because we're going to put our 0 point wherever our rotational axis is. And there's actually a problem in the homework where you do it somewhere along the length, and you got to put your 0 along at that point and then integrate. So the only difference is where we start and where we end the integral. And it gives us a different answer, 1/3 ml squared, right? So, so in the problem that they give you in the homework, they have you rotated around some point somewhere in between here. And in that case, you just put your 0 axis, you put your coordinate 0 or your origin at that point, and then you're going to integrate from negative something to positive something according to where you've placed your 0. Now, here's an interesting thing is that, and that this comes from what we just did. It's called the parallel axis theorem, and that is that if you have two rotational axes that are parallel to each other, then you can actually use moments of inertia. You can use different moments of inertia to create a total moment of inertia. Now, what does that mean? Here we have. Let's see if we can. So yeah, here we have a situation where we have a long thin rod that's rotating around this point A, and then there's a disc stuck on the end of this rod that's going to rotate with the rod. It's been nailed to it or welded to it or something. Well, the disc is like a mass on the end of the rod, but it's not a point mass. So you can't just consider it a point mass that's going around in a circle, because it is actually a disc. And the disc, as it goes around the circle, it actually rotates. It has a very slow rotation as it goes all around, right? This end of the disc is on the bottom, but when it's up here, it will be on the top, right? So that disc is actually rotating as it goes around here, and we have to take into account that rotation. You have to do something with that moment of inertia of that disc. And what the parallel axis theorem says is that if we have this disc that's rotating at a parallel axis, so the axis that this is rotating at is parallel to this one, because this one's coming out of the page and this one is coming out of the page as it slowly rotates around. Then we can take the moment of inertia of this mass as if it is a point mass. So we take the moment of inertia of the center of mass as if it's a point mass. So this one would just be m times r squared, or m times the distance to here squared, which would be L plus the radius of this disk. And then we add to that the moment of inertia of this disk around its center, right? So we add to the, let's see, is it? They're actually doing it the other way around, actually. So the first one is the center of mass one. So they're taking the center of mass one to be the first one. So that one is 1/2 times the mass of the disk times the radius of this squared. So that's taking the moment of inertia of the disk if it was rotating around its own center of mass. But then they add to it this disk as if it was a point mass at some distance away from the center of the actual rotation at A. And so that one becomes m mass of the disk times the length, which is the distance to the disk, plus the radius that takes us to the center of the disk. And then you square that total amount, right? And that works for any object that is rotating off axis from its own center of mass axis, right? That even works if you just have this thing, if you just have this disk rolling. So it's rotating around a point at distance r. So if you have a disk like this, like a wheel that's rolling along, the wheel is not actually rotating around its center. It's actually rotating around this point here. It's actually doing this. It's like going around and around like this, right? So this is the situation we're dealing with. Instead of throwing a nail through the center of this and causing it to rotate there, we throw a nail through the bottom of it and have it rotate there. And we'll see if that makes a difference. Does that make a difference in this case? Well, according to the parallel axis theorem, our I of this parallel axis will equal the I around the center of mass of the disk plus I around from this point here, right? So that's the I at some distance d, which we'll call some distance d there. So the moment of inertia around the center here for a disk is actually let's see here. They actually tell us the center mass of the it's 1/2 mdr squared, just like it is in this other one. So that first one is 1/2 mdr, 1/2 mass of the disk times the radius of the disk squared. And the next one would be this distance here. So we're taking the mass of the disk at the distance r squared, because that's the total distance to where it's rotating around, r squared, right there. This would be the disk. This is the moment of inertia of the disk rotating around its center, but this whole thing is the moment of inertia of the disk rotating around its edge, right? So it does change it. This is going to be 3/2 mdr squared instead of 1/2 mdr squared. So it has more moment of inertia. So that's what this is all about here, is this parallel axis theorem. This also works for things like, let's see, let's give you some other examples. This works if you have like a merry-go-round. If we have a merry-go-round and if we have a kid standing on the merry-go-round, and if you treat the kid, instead of treating the kid like a point mass, you treat the kid like a cylinder, like, because a child is more like a cylinder than they are like a point mass. And so you have this like cylinder that's standing up on the edge of this thing, right? Then what you would do then is you would take to get this total moment of inertia of this thing. Well, a better way to say this, to get the moment of inertia of just the kid, you would take the moment of inertia of the cylinder as it rotates around its center of mass, and you go look that up or do a calculation for that. And then you would add to it this mass of this cylinder at the distance it is from the center of the merry-go-round. Then if you wanted to add the merry-go-round moment of inertia in there too, you would add in the moment of inertia of this big disk, which is the merry-go-round, right? So these moments of inertia add together as they rotate together. Parallel axis theorem. Let's take a look at some other. Oh, and here we go. We have a person on a merry-go-round as our problem here. So here we have a 25 kilogram child standing at a distance r equals 1 meter from the axis of rotating merry-go-round. Merry-go-round can be approximated as a uniform solid disc with mass 500 kilograms and a radius 2 meters. Find the moment of inertia of the system. Now they're going to assume that they're going to go ahead and use this kid. This kid will be a point kid, I guess. Yeah. So they're going to assume the kid is kind of like a point mass rotating around here. But I would say that they're more like a cylinder than a point mass. In this case, they're going to take the total moment of inertia for this is going to be the moment of inertia of the rotating disc, which is 1/2 times the mass of the merry-go-round times the radius of the merry-go-round, right? So that's this one right here. And then they take the moment of inertia of the child and they just add them together. That's not actually, I mean, it is technically the parallel axis theorem, I guess, but it's not really how we think of the parallel axis theorem. This is just the sum of two things rotating together, I think. If you were going to approximate the kid to be a cylinder, then instead of the moment of the inertia of the kid being just the mass of the kid times the radius squared, you would have a very much more complex thing. You would have the mass, and you would have the moment of inertia is equal to the moment of inertia of a cylinder that has the mass of a kid, plus the mass of the kid times their radius, times this radius, which is their distance to the cylinder that is the kid, plus the radius of the cylinder of the kid, which is representing the kid squared. And then you would add that to the moment of inertia of the disc, which is the merry-go-round. And you can even get more detailed with this, quite a bit more. This merry-go-round obviously has many different parts to it that are not massless, that are going to add to the moment of inertia of this merry-go-round. So you have all these bars. Each one of these bars is like a bar rotating around its end. And we've already done the moment of inertia for each one of these bars. So we would take 1, 2, 3, 4, 5, 6, 7, 8 bars, whatever their mass is, and use the formula that we had before from a bar rotating around its end and add in 8 of them, right? And then we also have these crossbars here, which we could add in. And now they're at angles, and that's going to be more complex. But then we have these bars that go down this way. And each one of those is like a cylinder, like the kid, that's rotating at some distance r away. And so they would have a moment of inertia that we would use by that we would add in by putting together the moment of inertia for a bar rotating off axis using the parallel axis theorem. So two things here that we've learned about, well, three things that we've learned about moment of inertia. Moment of inertia. Let's write down the three things we've learned from the moment of inertia. The moment of inertia of a single point mass rotating at some distance r from the point of rotation is the mass of the point mass times the distance to the axis of rotation squared, right? That's the first thing we learned. And we also learned that we can use this in an integral. We can calculate this using an integral, and the integral ends up looking like this, where we're going to integrate over a shape, and we're going to integrate r squared dm, right? So we learned that already also. Then we learned from this problem here, we learned that if you have two things rotating together, and they each have moment of inertia I1 and I2 separately around the same rotational axis, then you can add those moments of inertia together. These moments of inertia have to be calculated around the same rotational axis, but you can add them together, and you can have many more. You can have 5 or 6, and we learned that already too, and that's your total moment of inertia there. But then we also learned the parallel axis theorem that says if you have two things that are rotating and their rotations are around parallel axes, then you can actually take the moment of inertia of this is not two things rotating, this is one thing rotating. If you have one thing that is rotating not only around a particular rotational axis, but also around its own center of mass, so it's off axis, then you can take the moment of inertia around the center of mass of that object and add it to the moment of inertia as if it's a point particle rotating around some distance d from the parallel axis, right? Call it d parallel. And again, what that means is that if you have some object, so this is your axis of rotation, you know, and well, that's a bad way to, let's look at it from above so that it looks like a point. So there's your axis of rotation, and you're a disc or you're a cylinder or you're a sphere out here, and you're rotating around this axis. Not only you're rotating around it like a point mass would, but this thing here can be rolling or rotating around its own axis as it goes around, right? Kind of like the Earth rolls around its axis. So then you have to consider the moment of inertia of that rolling motion, or that separate parallel axis rotation. So hopefully that's clear enough. There's a lot of stuff going on there when it comes to rotation. It gets a little complicated. But here we go with the sphere on the end of a solid rod. We're doing this rotation thing. Now, in this case, we have a rod that has moment of inertia I, right? This rod right here is rotating around its endpoint, so it has a moment of inertia of the rod. This sphere is also rotating around this same point, but this one we're going to have to use the parallel axis theorem, because it's an object that has some shape to it that is rotating parallel axis. So here's the axis it's rotating around as a sphere, but as it rotates, since it's connected to this rod, it's also going to be rotating more slowly around its own center of mass. So and again, just to illustrate this, because I'm not sure if I've illustrated well enough, but to illustrate this, if you painted this side of the sphere, just put a big splotch of paint there, here in this position, this paint is down here. Over on this position, the paint is on the outside, on the right side of the sphere. At the top, the paint is on the top of the sphere. So this thing is obviously rotating, because this thing rotated to here, this paint rotated up to here, and when you go over to here, it'll rotate over to this side. So the sphere is obviously rotating around its center of mass. It's just a very slow rotation that is in line with the rotation of the whole thing going around, right? So that is definitely rotating. That means we need the parallel axis theorem to be involved. So that means that we have to add to this. This is the moment of inertia of the rod, but instead of just adding to it the moment of inertia of the sphere, we have to add to it the moment of inertia of the sphere according to the parallel axis theorem. So the parallel axis theorem says that this will be the moment of inertia of the sphere itself around its center of mass, sphere center of mass, plus the moment of inertia of the sphere as if it's a point particle around the parallel axis A. This is the parallel axis A. So this second one is always just the mass of the sphere times, or the mass of the object times the radius times the distance to the sphere. In this case, it would be the L. It's this distance to the center of the sphere. So you have to do L plus the radius of the sphere R, and then you square that. That's what that one always looks like. This one, you have to figure out what the moment of inertia of a sphere is, and thankfully they're going to tell us that. We'll get around to that here in a minute. So we're going to have both of those things involved here. And as we go through this example, we can see that that is the case here. We're going to have the moment of inertia of the rod plus the moment of inertia of the sphere. The moment of inertia of the sphere is going to be the I of the center of mass plus the mass of the sphere plus L plus R squared, right? Times L plus R squared. And so they do the parallel axis. That's the parallel axis theorem. And then once they've done the parallel axis theorem, then they can add the moment of inertia of the rod to that one that they just calculated from the parallel axis theorem. You get these three terms involved. You combine all the terms, and you get one final answer here. In part B, I don't know what they're asking in part B. What are they asking in part B? I don't know. Oh, here we go. In part B, the center of mass of the sphere is located distance r from the axis of rotation. So they're doing this is a different distance, I guess. Yeah. So anyway. So this actually brings us to a point where we're going to do some other examples, and we're going to calculate the angular velocity of a pendulum, for example. So we have this pendulum that's in the shape of a rod that's released from rest at an angle of 30 degrees, has a length of 30 centimeters on mass of 30 grams. What's the angular velocity at the lowest point? And we're going to use conservation of energy, conservation of rotational energy. So we have the conservation of energy equation says that potential energy is going to turn into to kinetic energy. In other words, the change in potential plus the change in kinetic is going to equal zero, right? There'll be no loss. The potential energy is easy. It's just mg times h. Now we have to use the h, the height of the center of mass of the rod, because that's how objects behave. Their center of mass obeys these laws. And so that ends up being mass times 2g times L over 2 times cosine theta when we pulled it sideways like that. Finding the center of mass of the rod distance is that geometry. Then we go ahead and plug that into our equation. So mass times g times L over 2. And we've got that one. We've got, let's see here. We actually wanted, at the top of the swing, the bottom of the swing. Oh yeah. So they actually do it. They do both the top and the bottom of the swing here. I didn't see that they'd calculated the bottom of the swing one. But so here we have moment of inertia of the top of the swing, mgl over 2 cosine theta. But at the bottom of 2, it's just mgl over 2 because that's this point right here. So this is mgl over 2. This is mgl over 2 cosine theta right here. So either way. So at those different heights of our swing, if we take the difference between them to get delta U, we take the final minus the initial, this is what we get. They've actually factored out the mgl over 2, so it's just 1 minus cosine theta here. And that actually, so this actually is probably a little confusing because, and so let me explain it a little bit better. I didn't explain that very well. Let's go back to this and take a look at what they're doing here. So in this case, they've swung the rod out here to its high point where they're going to release it, right? And so they're calculating that height of the rod here perpendicular across, which is L over 2 cosine theta. That's just because this is theta here, right? And this is the adjacent side, right? And the total length is L, the half of the length, which is what we're looking for, is L over 2. When it swings back down to here, then it's just L over 2 cosine theta. So the thing that we're actually calculating there, just in case you didn't catch it, the thing that we're actually calculating is this height. This is the change in height, right? So that's actually what we're looking for the rising of this thing and the lowering of this thing. So we're going to call this height 0 right here. We're going to call this height h, and this height h here is actually equal to this L over 2 cosine theta, not L over 2 cosine theta, just L over 2. And then you subtract off this thing, which is L over 2 cosine theta. So it's L over 2 minus L over 2 cosine theta. That's the height at the top. The height at the bottom of is of course 0. So you have a potential energy of 0 at the bottom, right? So that's where this comes from, if that confuses you, because they calculated two different potential energies, and then they took the difference between the two for the top potential energy, which is this one. This is your final potential energy. This is your initial potential energy, final minus initial, right? And so it starts off initially at the, they're actually, I guess they're actually saying 0 is actually at the top, and then they're saying this is at the bottom. Doesn't really matter which way. But so they're saying that this is the initial. They're starting it up top, and then they're swinging it down to the final minus initial right there. Then when you take final minus initial of kinetic energy here, for the change in kinetic energy, their final minus initial kinetic energy is, that's not right. What are they doing there? This is final minus initial. If it's initial, that should be, yeah, well, that's 0. Then their kinetic energy, initial kinetic energy should be actually, their final kinetic energy should be this one and not the other one. They did that wrong. I'm almost certain they did that wrong. I think that this is a typo here because they're getting well, let's see here. I think that should be the other way around, but I must, if I'm missing something, then you'll have to figure it out. But in the end, you should get this equation. This is correct here, but I don't think if this is your final minus initial potential energies, your final potential energy is that means that you started at 0. You said that 0 was your top and your final was negative. So this should actually be a negative here, I think. And they should be switched, or these should be switched, one of the two. It doesn't matter which one is switched. But anyway, I think that they made a mistake setting up the equation, but they made the mistake in such a way that it doesn't come out wrong. They made two mistakes that righted each other, I think. But anyway, the point is that this is the final equation you're looking for, where you essentially have your final kinetic energy equaling your initial potential energy. So this was your initial potential energy. This is your final kinetic energy. And that is correct. That's what it should be. All the potential energy turns into kinetic energy. Well, then you just solve for omega, and that's quite simple. And then you plug in numbers, right? So no big deal. All right, so that takes us through that section. And then we move on to torque, learning about torque. Remember that in two previous sections ago, we actually had a bunch of chart a bunch of moments of inertia, and those are all calculated from taking volume integrals around different shapes, different volumes, right? So these are things you want to remember where they're at, so you can look them up for different moments of inertia of different objects around different axes, because we're going to use that a lot. The next section we're going to learn about torque. Well, torque is what happens when you apply a force to an object and it causes the object to rotate, right? So if you apply a force to an object that causes it to rotate, then we can calculate this thing called torque, which gives us an idea of how the rotation is going to occur. So you have a door like this with the hinge here and the handle here. If you apply a force to it, it's going to cause the door to rotate. And depending on how much force you apply to it, that determines how much it's going to rotate, how fast it's going to rotate. So if you apply less force, it's going to rotate less, right? However, it also depends on where you apply the force. And we've talked about this. If you apply the force closer to the hinge and it's the same force as before, it's not going to rotate as much because it's harder to open a door when you're closer to the hinge. And also, if you apply it at an angle, it's not going to open the door as much. You've probably experienced this trying to open the door for somebody who needed to get through, but you're holding the door near the hinge or something at an extreme angle. It's hard. You have to push really hard to keep that door open. So the angle matters. And it turns out that this is a cross product relationship. We're going to define the torque as a vector of that is the cross product of the distance from the distance cross product with the force. And how do we calculate that distance? Usually we calculate that distance from the point of rotation, from the axis of rotation, but you don't actually have to. You can measure it from any point you want to, but you have to use the same point for all torques in the problem that you're doing. So you can't just mix up the point you're measuring your torques from. So here's an example of a force that's being applied at some distance r from some origin. We're just going to use the origin as our point for calculating these torques. So there's your r vector, there's your force vector. And remember, the right-hand rule tells you the direction of the torque. So the torque is going to be 90 degrees both to the R and the force vector. Put your hand in the direction of the R, turn your fingers in the direction of force, R cross F, and your thumb will point in the direction of the torque. So this torque is straight up in the Z direction. If you want to calculate the magnitude of the torque, we know how to do that for a cross product. It's R times F times sine theta. And this really shows you how the distance matters, right? The distance matters, R times R and R matters. Shoot, can't highlight that, I forgot. So R matters, that's the distance where you push on something matters. The force matters, that's how hard you're pushing, and the angle that you push at, which is theta. That all three of these matter when you're figuring out how to use a force to rotate something. And that shows up in the torque equation. If your distance and your force are perpendicular to each other, or you just know the perpendicular distance to the force, then the magnitude of the torque is just the perpendicular distance to the force times the force, and that's easy enough. Okay, so here's an example of if you got a disc here and you're pushing on the disc or pulling on the disc at this angle, you say you tied a rope to the disc here and you're pulling on it at this angle, then you can use the axis of rotation as your measuring point and measure a distance R to F here, and then do the R to cross F magnitude, which would be RF sine theta. That'll give you the magnitude of your torque here. And then the right-hand rule says that R cross F, and I guess if I'm doing it the way you guys are seeing it, I don't know if my camera will do it backwards for me, like this. So R, right? And my fingers don't bend that way. I'm gonna have to use my left hand. It's gonna have to be R, there we go, R, and then cross F, and then my thumb is coming out of the page at this point, right? So I guess I could do it this R, F, and the thumb do R, there we go. If I go R, F, and then the thumb's coming out of the page. There we go, that's how that works. So I have to do the right-hand rule backwards. So but R, and then F, and then that vector is coming out of the page, right out of the screen there for you. And then you've got the position or the direction of your torque coming out of the page. If you have multiple torques going on from multiple forces, you can just calculate them separately and add them together. As long as they're all measured from, as long as the distances to those forces are all measured from the same point, you can add the torques together just like that, no problem. So here are multiple forces acting. Notice that they haven't put any shape that they're acting on or anything that they're acting on. They're just multiple forces acting. And you can actually calculate total torque from this by measuring from you can measure from 0, you can measure from 2, 0, you can measure from -2, 2, -2, -2. You can measure from any point you want. Choose a point and measure all your distance from there, and then calculate all the torques and add them all together. No matter where you measure from, you can measure from this point here, out here. No matter where you measure from, the sum of the torques will always be the same number. Why would that be? Well, if you move these numbers around, some of these torques are going to decrease and some of them are going to increase. Some of them are going to change direction and some of them are going to change direction the other way. So it'll always work out no matter what point you measure your distances from. We usually measure from the origin or we measure from the axis of rotation just because it's convenient, usually, often. But it's not always the best way to measure torques from. Sometimes in a situation, you'll want to measure the torques from a particular point in order to eliminate the number of calculations you do. Because let's say that we're not interested in anything that this force is doing, but we still have to calculate our torques and have to include that in it. So if we're not interested in what this force is doing at all, then we could actually measure our torques from this point, 4, 0, and this torque wouldn't even be in the calculation because the distance to it would be 0. So the torque from this force would be 0. There are many other situations, and let me show you another situation that is pretty common. So let's say that we're leaning a ladder against a wall like this. So you've got this ladder leaning against the wall. of the ladder leaning against the wall, there's a normal force on the ladder this way. There's the weight of the ladder this way. There's friction on between the floor and the ladder because the ladder is trying to slide out this way. So there's a frictional force this way. Against the wall, there's a normal force from the wall. Here, there's also this ladder's trying to slide down this way. So there's a frictional force this way. So there's lots of different forces. If there's a person standing on the ladder, then there's the weight of the person on the ladder, you know, like this, like this and all this stuff. So there's lots of forces on this ladder. And let's say that I'm interested in the frictional force against the wall this way, but I'm not interested in anything else. Well, then I would probably choose my point for measuring the torque maybe at the bottom here so that the torques from these two forces become zero. Let's say I don't even know what those forces are. But if I put that down there, the torques from them will be equal to zero, and they won't figure into anything. Or I could do it here or here to eliminate those two forces, but you definitely wouldn't want to do it here because that would eliminate this force from the torque equation or from the torque calculation. You don't want to remove that because that's something you want to learn, you want to know. So you keep it there. So that's kind of a preview into how you might use this. We'll see more why that's the case as we move on. Anyway, we do this one, we calculate the torque for each one of them separately and add them all together, and they do that here, torque 1, torque 2, torque 3, and torque 4. I didn't count the first one. They calculate all those different magnitudes, but they also are, at the same time, they're determining the direction. So the direction of each of these torques is either going to be out of the page or into the page, depending on the right-hand rule, right? So we have RF this way, so that's R, let's see. Yeah, that's RF. So it's coming out of the page for this top one, this 20 Newton one. For the 40, the R is pointing out to the right. So we go out to the right, R, and then turn the hand up for the force F, and it comes out of the page. So this one is out of the page as well. And then for this one, at the bottom, we have R going out for 30 Newton rather, the 30 Newton force, we have R going out to the left, and then we turn our hand downward a little bit, and that one's coming out of the page as well. And then this bottom one here, we go straight down with R, so that's R straight down, and then to the left, and that one's also coming out of the page. So all these are coming out of the page, apparently. No, that's not right. Did I do that last one right? That one's R and F. That's actually into the page, right? So that's into the page. Anyway, so this one's into the page. These three are out of the page. And into the page is going to be the negative z direction. Out of the page is actually the positive z direction. So they get three of these being positive. The first one, these three, and then this one being negative. And when you add those total momentum, all those total together, those total magnitudes together, you get 230 Newton meters. Notice that torque is Newton meters because it's force times distance. And that's fine. And then the direction, of course, is positive, which is out of the page. So that's good. Here they're calculating the torque on this object here. And again, it's just three different forces. This one right here is going to have a perpendicular distance equal to 0 because the force goes right through the center. And we actually have a name for this. We call this the line of action. So the line of action is the line that if you extend the line of force, that's the line of action, right? The line of action of a force, when it passes through the point that you're measuring your torques from, that means that that force will have no torque relative to that position, relative to that point. So this force is actually 0 distance away from this point perpendicularly. This one, of course, is not. That's the line of action of that one. This one is also not. This is the line of action of that one. So they definitely have distances to that point. But this one goes right through that point. It doesn't have any torque from it. And then you can see that they do that here. They get the torque from 1, the torque from 2, and then the torque from 3, which is 0 because it doesn't have any distance. You can also think of the angle between this and the R vector. The R vector is always going to go from the point that you're measuring from towards the force, and the angle between these two is 180 degrees. And the sine of 180 degrees is 0. So RF sine theta will be 0. And that's another way to calculate that or to understand that. So they calculate those, they add them together, and of course they're giving them signs, positive, negative for out of the page, negative for into the page, for these two forces that are in the plane of the page. Here's another problem where they're going to apply this force here, and they're going to rotate this thing here, right? They're going to measure the distance probably from this point down here all the way up to there, 100 meters distance with the angle and all that. Another similar problem. Now, the interesting thing about torque is that if you actually take your Newton's second law here and you plug in r times alpha, the rotational acceleration times r, which is equal to kind of the tangential acceleration for rotation, in rotation. If you replace that a with r times alpha here, you get force equals mr times alpha, and mr is actually I in the end. Well, how is that? Well, if we multiply r times f, multiply r on the left side, so we get r times f, then we have to do that on the right side, we get mr squared, right? And this rf is torque, because r times f is torque if r is perpendicular to f. So we're gonna say that this is perpendicular, and that's gonna be torque. And in that case, we get mr squared on the right, which is definitely I, right? So this mr up here becomes I through just a little algebraic manipulation. And then we get a new equation, torque equals I times alpha, which we can think of as Newton's second law for rotation. Instead of force equals mass times acceleration, we get torque equals the mass distribution kind of thing times rotational acceleration, right? Alpha. So that's Newton's second law. And you can add many torques together on a single object, and it will equal the moment of inertia, total moment of inertia of the object times its angular acceleration. So you can use it in all the same ways we used Newton's second law before. And here they show this in vector form and show that it is true in vector form, which it is. So if we're dealing with forces now and rotation and acceleration, then what we're going to do is we want to be able to write down all of our forces, make sure that we have all the angles correctly. Then we need to calculate all our torques relative to some point, and then we can actually set that equal to I times alpha, the moment of inertia of the total system, times the acceleration, the angular acceleration of the total system. So we go back to our merry-go-round problem, and we have a person that's going to apply a force to this merry-go-round. That force is going to create some kind of torque, and that torque is going to create some kind of angular acceleration due to the relative to the moment of inertia of the merry-go-round. So we're going to just call the merry-go-round a solid disk, so it's going to have a moment of inertia 1/2 mr squared from the table previously. And then let's see, do they have a kid on this thing? No. Okay. And that's fine. So they're calculating that moment of inertia, 56.25 kilogram meter squared. Then the torque is equal to r times f sine theta, so they can actually calculate the torque because they've given us the radius and the force that's applied, so we can calculate that to be 375 newton meters. And from Newton's second law, we can calculate alpha because it equals torque over I, torque over moment of inertia. So that ends up being 6.67 radians per second squared. What if we add a child on? They are going to add a child on, so we can calculate the moment of inertia of the child as a point child. So it's mr squared, and then we're going to add that child moment of inertia to the moment of inertia of the merry-go-round. So the total moment of inertia of the system is going to be 84.38 kilogram meters squared. And then we plug it into Newton's second law again to calculate for a different angular acceleration, which is actually less, 4.44 radians per second squared instead of 6.67 radians per second squared. And you would expect that with the same amount of force, and this, which would be the same amount of torque, but a different moment of inertia because you have more mass situated differently, you would expect less angular acceleration, which is what we get. And that is Newton's second law of rotation. You can also do this for things that aren't rotating. So if things aren't rotating, you can actually get a, you can also get a situation where you have something like this, a bunch of forces acting on a disk to try to rotate it, but it's not rotating. So we have forces coming in from all angles, all different kinds of forces all coming in here, trying to rotate this thing, but it's not rotating. In that case, the sum of the torques equals I times alpha, and alpha equals 0. So the sum of the torques equals 0. So if you have torque, if you have force 1, force 2, force 3, force 4, then you get torque 1 plus torque 2 plus torque 3, and so on and so forth. Add those all together, and they have to equal 0. Well, in one of those torques, you might not know something. You might not know its angle, or you might not know the force. And if you don't know one of those things, then maybe you can use this equation to solve for it. You might have to use something else to solve for it, but you might be able to use this to solve for it. There's also a situation where you might encounter. Let's say that we have some object, so whatever it is, and we're pushing on it from all different angles with different forces. So we have a force this way, 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 whatever. All these different forces, right? That are acting on this force 1, force 2, force 3. They all have different angles, force 4, force 5, force 6, whatever. This also can have linear motion. So it could actually be moving, up this way with some velocity, or down this way or whatever, but it could also be rotating as well, right? It could have rotation and movement. Well, we don't generally deal with rotation and movement. Well, we sometimes do, but we'll do it in very specific circumstances. But what if it's not rotating and not moving? Well, then you get extra equations. And even if it is rotating, so in either situation, whether it's moving and rotating, or not moving and not rotating, or if it's rotating and not moving, or whatever else, you actually get multiple equations from this, because you're always going to get the sum of the torques equals I times alpha for the system, but you will also get the sum of the forces in the x direction equals the mass times the acceleration in the x direction. If it's not accelerating, then it's the sum of the forces in the x direction have to equal 0. You also get the sum of the forces in the y direction have to equal the mass times the acceleration in the y direction. And in the z direction, if it's three-dimensional. So you get old Newton's laws equations, but you also get new rotational Newton's laws equations, right? So while this seems like it's getting more complicated, we're also giving more tools to solve for problems. So you have help there. All right, so now we're going to go on to work and power for rotational motion. So remember the work is equal to force times distance, the dot product, R dot F, or F, sorry, F dot R, anyway. It's a dot product between force and distance, and essentially tells you how much energy is required to move something by applying a force to it over some distance, right? Well, they go through the math of this. When it's rotation, not only do you have force just times distance, but we have rotation now. So we're going to end up with cross products that relate distance. So our distance is now going to be a arc length. It's going to be a distance around a rotation, in other words. And that's going to be related to the radius and the angle. So we do that work. And then to calculate the dot product between our force and that arc length, force dot ds, we're going to have to plug in the d theta cross r, because this is a rotational thing. So we end up putting that in, and we end up doing a little bit of math, a little bit of the FOIL theorem, you could think of it as, not FOIL rather, but distribution property, the distributive property, not FOIL. But anyway, they go ahead and do this math, and this is what they end up with. And it turns out that one of these things, the R, goes with the force and makes the torque, and with that cross product from this distributive law of vectors. But we end up with the torque dot product with the angle, right? So now we have something that looks very similar to the work linear. The linear work was force dot product with the distance. This is torque dot product with the angle. Well, that's nice because it's simple. right? We can take a little piece of the work and add up all the different torque dot angles together and get that. And we realize also that the dot product only works when the torque and the angle are pointing in the same direction. So these two, this torque and this angle are pointing in the same direction. We're now calculating just that scalar version of the work, because work is a scalar. So and you can actually use this. You can actually use this to calculate how much work is done in rotation when you're applying a torque, and that's fine. But the real interesting thing about this is where it fits into the work energy theorem, because the work energy theorem says that we have some work that's being done and that changes the kinetic energy. So kinetic energy at B minus kinetic energy at A is equal to the work done from A to B. Kinetic energy is actually going to be equal to 1/2 I omega squared, very similarly to linear kinetic energy equaling 1/2 mv squared, right? We're replacing the m with I, because it's rotational. We need to know where that mass is. We're replacing the linear velocity with the angular velocity, omega, right? So it looks very similar. And we can actually show that that's true. It's not that hard to show that that's true. I don't know if they'll do it in here. They should. Yeah, they're. No, maybe not. Looks like they're not going to do it. But it's not that hard to show, actually. The only thing you need to do really is to take this. Where did it go? Oh, there we go. All you need to do is take the kinetic energy, linear kinetic energy, and replace V with R times omega, because if V is tangential, then it equals R times omega. And then you get R squared omega squared, and then you get M R squared times omega squared, and MR squared is I for a differential piece of material. And then you get this. So it's not that hard to do. But anyway, you can just take it as is, and you know that the rotational kinetic energy is now 1/2 I omega squared for some object that's rotating around a point that gives this particular moment of inertia. Then we can actually create a new work energy theorem that includes rotational kinetic energy. So essentially what's going to happen is the kinetic energy in the work energy theorem is going to contain linear kinetic energy and rotational kinetic energy. You have to include them both. Now, if there's only one of them, if there's only rotational kinetic energy, you don't have to worry about the linear kinetic energy. And vice versa. But if you do have both, like in the case of a rolling wheel, then you would have to use both kinetic energies equaling work. So in this case, we're just going to use rotational kinetic energy. We're going to have some work that's going to cause some rotation through some angle. And they tell us the torque that's being applied to a flywheel. They tell us the moment of inertia of that flywheel. They tell us the initial angular velocity. They want us to calculate the final angular velocity. And they also tell us how much angle it's going to rotate through, 8 revolutions. So in order to do this problem, we write down our work energy theorem, which is going to be, this is our work energy theorem down here, actually. It's going to be work is equal to 1/2 I omega squared minus 1/2 I omega squared at the 2 different points, right? That's our work energy theorem. But we also know that work is equal to torque times alpha, right? Because work is normally equal to force times distance, so now it's equal to torque times alpha. So it's torque times alpha final minus torque times alpha initial. That's that right there. So we put those 2 equations together to make this equation. And we know the torque, and we know, sorry, I said alpha, but it's theta. I meant theta, torque times theta, not torque times alpha. But anyway, we know our final theta and initial theta because we know that it goes through 8 revolutions. There's 2 pi radians per revolution. So 8 revolutions is 16 radians, and we start at 0. We go from 0 to 16. So 16 minus 0 gives us 16 total for our difference in theta. We multiply that by our torque, 12 newtons. Why can we just multiply it? Because they're going to be perpendicular to each other, because it says right here, well, they don't actually tell us that. We're assuming that. But we're assuming that, so a flywheel is like a wheel. like a disc like this. And we're going to assume that we're going to be pushing on it to rotate it. We're going to push on it like this, which would be perpendicular to the R, because the R would be measured from the center of the flywheel this way. So those two would be perpendicular. So it's an assumption we're making. Maybe it's not the best assumption, but they should have made that clear. But anyway, that's why we can just multiply toric times theta and not have a sign of the angle between them after that. But anyway, once we've got that in there, then we need to know we need to put this in our equation with i's and omegas. So the i's are 30 for both of these, I 30, I 30 for both of those. But the moments of the angular momentum, or the angular velocity is different, because they say that we start at 0, so the second one becomes 0, and we end at some thing that we're trying to calculate, which is we're going to call omega at b. So then we've got our equation built up. The left side has the work done. The right side has the difference in rotational kinetic energy. We solve for omega b, and we get 6.3 radians per second after 8 revolutions. They do the rotational work of a pulley here. So the rotational work on a pulley, you're applying a force with this rope over this pulley right here, right? And that force is going to be equal to a torque, which is torque times theta. Sorry, is going to be equal to a torque, which is R times F, right? And then the work from that torque, that force is going to be torque times theta, because it's 90 degrees. And then the difference in kinetic energy again here, and then that's going to be equal to this work being done, and then again we're going to calculate for that final omega. So not really any different from the previous one. Power for rotational motion. Power is just the work in time, right? It's the derivative of the work in time. So if you do this math, you end up with torque times the time derivative of theta for the power, which in the time derivative of theta is actually omega. So this ends up being torque times omega for the power. Torque times angular velocity. So in this case, we know the engine is operating at 9.0 times 10 to the 4 watts. So that's our power. And they're telling us omega, 300 revolutions per minute, which we're going to have to convert into radians per second. So they do that conversion here. There's your power. Then they solve for the torque, 2,864.8 Newton meters. And that's it. Here they show all the rotational and translational relationships. Here they show the kinematic equations. Here they show the dynamics equations, right? For rotational and translational, all the different relationships, and then we're done with the chapter. So hopefully that gets you enough to get started on your homework, and please send me your questions and I will answer them. I'll be around all week. Have a good Thanksgiving.